Okay, so we're going to look at the derivatives of logs then. So obviously we know logs, kind of inverse of exponentials, they have a particular rule. It's in our log tables, ln of x equals 1 goes to 1 over x when we differentiate. So where x is, I suppose, an expression, a variable, okay? If we have, and we will see it come up, if we have a case of ln of a number, that is actually all just a number. We could evaluate that to a number. So if I differentiate it, it's just going to go to 0. Okay, so that's one to watch out for. If I have the derivative of ln of just a number, that's just going to go to 0 because there's no x part, there's no expression element to that. When we're doing our logs, kind of similar to our exponentials, we have the derivative of the log and we get the derivative of the expression within the log, okay? In fact, it's probably more similar to our trig ones because we can it's set up in a similar way. We have our x expression there as kind of like the subject of our log. So let's just look at a few of these in practice. The other thing that we need to really be fluent in is our log rules. Okay, so the two things I suppose to note here is we need to know our log rules, and lastly, we're looking at logs that are to the base e, which is generally called like our natural log. Okay, and it's ln. So ln. So in your log tables there, they use ln. That's our log to the base e. So all of these things very important for what we're looking at in this section. So ln of 3x plus 2. So I'm going to take my derivative here. First of all, I'm just going to apply my rule. So my rule says it goes to 1 over whatever's in that subject part, which is 3x plus 2, but I have to multiply then by the derivative of that part also. So I get 3 over 3x plus 2. So same as we would have done with all our trig ones, multiply by the derivative. To look at the next one, we can make use of one of our log rules and one of our indice rules. So to the power of, or the fifth root is the same as writing it as the power of 1 over 5. And using my log rules, I can rewrite that as 1 over 5 ln of x. And I can then use that to quickly find the derivative, which is 1 over 5 times 1 over x, which is 1 over 5x. Okay? So using your log rules there helps us to simplify it. We can of course do it without using our log rules and we end up at the same answer either way. The same thing can be said for this next one. Using my log rules, I can actually split that up as ln of 3 minus ln of x. And if I find the derivative, as I've said already, ln of 3 is actually a number. So when I differentiate it, that's just going to go to 0. Ln of x goes to 1 over x, so I get minus 1 over x. And that's just my answer, minus 1 over x. So making use of our log rules really helps us here to simplify these derivatives. I think in some of the examples there I have done it out the full way without making use of the log rules, but we can see here how much simpler it is if we just make use of our log rules. We'll look at one of the questions here. So the first question is from last year's paper, and this is it was quite a challenging question. I suppose particularly when we get into the second part of the question. But let's just start it off. We can see we have two expressions. We're going to have to use a product rule. Let's call u this one. Let's call v this one. So u is equal to tan of x over 2. Okay, which if we remember x over 2 would be the same as a half x. So let's just kind of have that in our head as well. And then v is going to be ln of x. Let me find my derivative for each of these. Then du dx is going to be sec squared x over 2. That's me differentiating the function. Okay, the function part, but let me use a different color there because we're using green already. So that's me differentiating the function part. So tan goes to sec squared, but I also have to differentiate my angle part, my x over 2. So I'm going to multiply by a half. I'm going to multiply by a half. dv dx then is just going to be 1 over x. Putting it all together then using my product rule, it's u dv dx plus v du dx. So let's sub everything in appropriately. U is tan x over 2, dv dx is just 1 over x, plus v, which is ln of x, times du dx, which is sec squared x over 2 times a half. Okay, so let's put it all together, I suppose. So I will have half tan x over 2 plus a half ln of x sec squared x over 2. Now, we've been asked in this case to find the value of the first derivative when x is equal to pi over 2. So x is equal to pi over 2. Now, the first issue I can see here is the issue of this sec squared. And if we look at our trig rules in our log tables, our trig identities on that trig page, we will see that sec is the same as 1 over cos x, which means, of course, sec squared would be 1 over cos squared x. Okay, so making use of that, we can apply our substitution of our pi over 2. So let's pick a color here, use blue, just make it a bit thinner there. So we're going to have pi over 2 all over 2 plus a half ln pi over 2 sec squared. We're going to rewrite using my rule over to the side here. I'm going to rewrite that as 1 over cos squared x over 2, and we know that for x we're putting in pi over 2, so pi over 2 over 2. Okay, so just rearranging my question to suit what I can do on my calculator, what I'm able to evaluate on my calculator, as it were. Okay, what I'm able to work out for myself. Okay, just noting there as well, that should be an x from our first part. Okay, so we're doing good, we're doing good. So here I'm getting 2 over pi tan pi over 2 divided by 2 gives me pi over 4 plus a half ln of pi over 2, so it's just going to stay as ln of pi over 2, 1 over cos squared, and again pi over 4. So evaluating each of these parts, I get 2 over pi, making sure our calculator's in radians also. We have to be in radians because we're working with trig angles and our angles in terms of pi. Tan of pi over 4 is just 1. Okay, tan of pi over 4 is just 1. I've been told, or I've been allowed, or I've been kind of informed in the question that my answer is going to be in the form where I still have ln, so I don't need to work out the value of the ln. 1 over cos squared pi over 4 in an end result gives me a value of 2, which is going to bring me to an end result of 2 over pi plus ln of pi over 2. ln of pi over 2. Okay, so that is our end result. That is our second derivative evaluated at that particular point. But we can see there the actual working out the derivatives, not the hardest part of the question. It was actually the evaluation that kind of could have caused issues there. Okay, moving on, we're going to look at a question then from 2020. We can see these ones kind of are cropping up. The ones to do with the ln are actually cropping up for us to work with. So in this question, it's not just ln of x, we have an expression in x, so I'm going to have to differentiate that part as well. So looking at the derivative of h of x, I have a half in front of it. We know that ln of x goes to 1 over x, so this is going to go to 1 over 2x plus 3, and I would also multiply by the derivative of that middle part, which is just going to be 2. So 2x, the derivative is just 2. So bringing that all together, I get an answer of 1 over 2x plus 3. Okay, the reason I don't need to worry about the c part is that c is a constant, which means that it would just differentiate to be 0. So that would just be plus 0 at the end there. Okay, that was just the first part of a question, so presumably it continued on and required you to do a little bit more. The next question here, I seem to have missed off the actual question, so I've just written in first here. F of x is ln of 3x squared plus 2, and g of x is equal to x plus 5, and we want to find f of g of x at x equals to a quarter. So we've kind of two elements going on here at the same time. So we're just going to take it step by step as best we can to make sure that we can kind of work the whole thing out. So f of g of x. So we should know that that means I take my function f, and what I'm going to do is instead of x in that function, I'm going to sub in g. instead of x, I'm going to sub in g, this x plus 5 squared. And now we're going to evaluate that. Okay, we're going to expand my bracket. So x squared plus 10x plus 25 plus 2. Let's keep working this out. So 3x squared plus 30x plus 75 plus 2. 3x squared plus 30x plus 77. Okay, now that we've evaluated the actual expression they want us to find, we need to find the derivative. Okay, sorry, it's supposed to be, of course, the derivative. There wouldn't be much point in us just finding that value. We're finding the derivative of f of g of x. So let's find the derivative of that. Okay, we'll give it a name. We'll call it h, for example. So if we call this function h, then h dash x. So for ln, we rewrite it as 1 over x. In this case, instead of x, I have this whole expression. So that's what I'll write in the bottom. 3x squared plus 30x plus 77. And I multiply by the derivative of that part, which is going to be 6x plus 30. 6x plus 30. So bringing that all together, 6x plus 30 all over 3x squared plus 30x plus 77. And I want to evaluate that at the point x equals to a quarter, when x equals to a quarter. So I'm doing 6 times a quarter plus 30 over 3 times a quarter squared plus 30 times a quarter plus 77. And if I evaluate all that out, I get an answer of approximately 0.372. 0.372. So again, maybe a somewhat challenging question, but we can actually see for the differentiation part of it, for the derivative part, we're following our rules as per normal. The hard parts here actually are probably coming in at this point. The substitution part, that's definitely a tricky element for us to do, particularly at this point. We would have done composite functions before, but we just haven't maybe expanded on them or revised over them in the same way. But we sub in our function g in place of x, evaluate that out, simplify it down, and then apply our rule to ln of x, making sure that we're just kind of keeping our head with those ln questions, okay? Making sure that we know that we're using ln of x as 1 over x, and if this x part is an expression, then that's what goes under here, multiplied by its derivative. Okay, we would have seen that notation in our notes when we did this in the book. So that's the general idea with our logarithmic ones. The only other thing I suppose to note is if the question gave you a log that wasn't to the base e, we would need to use one of our log rules to change the base. Okay, I didn't have an example of a question like that put in for us, but just to note, if we did encounter something like that, we may need to change the base. And the other thing to note with our log questions there was what I wrote at the start, and the idea of this part here being a constant value. What I mean by that is it means it's a number value. It's not dependent on x. So when we're differentiating with respect to x, that just goes to 0 because it doesn't change. Remember, your derivative's a rate of change. So ln of 3 is ln of 3. No matter what x is, it's ln of 3. So how does it change with respect to x? It doesn't. So it just goes to 0. So just important to watch out for all those little bits that could catch you out, because we should be able to get the derivatives themselves out fairly okay.